Okay, well, it's my pleasure to introduce Federico Castillo from Max Planck Institute. He's going to be talking about Todd classes of the permutohedral variety.
Okay. Hello, everyone. I'm very excited to be giving this online talk. Still trying to figure out some technical stuff about Zoom, but hopefully won't be much of a problem. Okay, so I want to tell you about, I want to spend a lot of time going over the motivation, because even though the titles seem to have some strange word, varieties and classes, we are trying to solve a problem, an enumerative combinatorics problem that is very concrete. So I will spend some time trying to explain the main question. So it all begins with a conjecture by Jesus de Lovera, David Haas, and Matthias Koppe. And they, in 2004, they conjectured that all matroid polytopes are Ehrhart positive. So let's first, there are a lot of words that you may not know. So I want to spend some time defining all of these words. What is a matroid? What is a polytope, a matroid polytope? Who is Ehrhart, and what does Ehrhart positivity mean? Okay, so first, very basic, what is a polytope? So this is, for today's talk, we can simply define it as the convex hull of finitely many points. We have dimension, phases. These are the 5 Platonic solids known since 2000 years ago. They are very interesting on its own. So we would like some enumerative questions about them, such as the phase vector, or the number of integer points that they will contain. But this is a very classical subject. These were known to the Greeks 2000 years ago. But what is Ehrhart positivity? So one thing that we are interested in is in counting the number of integer points. So if we have a polytope, say in 2 dimensions, so a polygon, such that all of the vertices, so it's the convex hull of finitely many points, but let's say that these points are snapped to the grid, we can count how many there are inside. So if P is the unit square, so we can count how many numbers, how many integer points of the grid P contains, and it's 4. And we can dilate our polygon and count the number of points that we get inside. In this case, we get 4. And in this case, when we dilate by 3, we get 16. So this is a function that we dilate by a whole number, and we count the number of integer points that we obtain. And this function, in this particular case, is not hard to see that it's actually, because this is a literal square, so it's t plus 1, there is a plus 1 there, depending on the dilation. So we always go t plus 1 squared. And that's the number of these black dots that we are going to get. In this case, you can see in this very simple example that this function turned out to be a polynomial in t. So it's t squared plus 2t plus 1. So Ehrhart proved this, again, this is from the 60s, that this is in general the case. So whenever we have a lattice polytope, and by lattice it means that the vertices are snapped to the grid, are really integer points, are black dots in the grid, even if you have higher dimensional grid. And if you are d-dimensional, then this counting function in which you dilate your polytope and count how many black dots you get, this behaves like a polynomial. So very concretely, there exists certain coefficients AD sub 1, or A1, A0. By the way, A0 is always 1. So there are basically D numbers that are unknown. And the idea, we are going to call a polytope Ehrhart positive if its Ehrhart polynomial have positive coefficients. Okay, these coefficients may be negative. You can force some of them to be 0. And so one thing that is part of the statement is that AD is not equal to 0. In other words, this thing has degree equal to the dimension of the polytope. Okay, so we call it positive if all of these coefficients expanded in this naive basis of the powers of t, if it is positive. Okay, that's a polytope. So what is a matroid polytope? So matroid has many equivalent definitions, but in this talk, a matroid is a polytope. So we have to define matroid polytope, and the definition is basically a 0-1 polytope. By this, I mean that all of the is the convex hull of finitely many points, but these points are all 0-1 coordinates. Okay, so not just integers, but 0-1. And with the extra property that all of the edges of this polytope are parallel to, so the edges are vectors, they are vector directions, one-dimensional vectors, and they all have to be parallel to roots of type A, if you are into that, or simply, another way of saying this, they have a very small support. So most of the entries are equal to 0, 1 is equal to 1, 1 is equal to -1, and that's it. The position of the 1 and the -1 can be anything. Okay, so these are polytopes characterized with two things. The vertices are very simple, just 0, 1 polytopes, 0, 1 coordinates. And the edges are simple, are roots of type A or these very concrete directions. And here, and after Vincent's talk, when we are thinking about polytopes, matrices have many different angles, but when you're thinking about the polytope and you think maybe about the space of all matroid polytopes, it turns out that they are really points in the type cone of something. And so when we buy them in bulk, you realize that the condition of being 0, 1 is not, it's kind of restrictive from the polyhedral point of view. It's very natural to ignore that and simply consider this all polytopes, and we are going to define a generalized permutohedron or a polymatroid, essentially the same in this talk, as any polytope. So we just erase the 0, 1 condition on the vertices such that all of the edges are parallel to roots of type A. So all of the, we want these special polytopes that the edges are particularly simple. And this is a definition of generalized permutohedron. It has several. This is also a kind of a definition of the base polytope of a polymatroid, the base polytope of a polymatroid. And let's do one example. So we don't need the coordinates to be 0, 1 anymore. And there are many examples. Let me just say one quickly, very related to what Vincent was saying. You can have the associahedron. So he was already talking about the associahedron. It's a polytope that, let's say, associahedron 4 will use 4 coordinates. It will have 14 vertices. They will be in bijection with triangulations of, in this case, an hexagon. And we draw an edge when these triangulations differ by a flip. So this is, this polytope has been studied many, many times. There are many different realizations, but this is not a combinatorial property. It's not about the phase lattice. One has to verify that the edges are parallel to the ones that, the edges of the type that I was asking. You can check that it is true. And this is a picture of this associahedron. Of course, this picture has to be projected to 3 dimensions because we are using four parameters, although the sum is fixed, so it's really 3-dimensional. And we can compute the Ehrhart polynomial, and by we, I mean Sage. And this, we obtain this polynomial. We have degree 3 as we should, we have this 1 as we should, and we have these 3 entries that are positive, so this guy is Ehrhart positive. Okay, so now we have all of the ingredients to go over the main conjecture again. So the conjecture is matroid polytopes are Ehrhart positive. Okay,
Federico, sorry to interrupt. So there's a question by Venkitesh about is a matroid polytope, how does it correspond to a matroid? Is it obtained from the indicator vectors?
Yes, so each vertex is a 0, 1 vector. And whenever you have 0, 1 vectors, you can interpret them as indicators function of something, because so you have a 0, 1 vector, say, of length 20. It's not just of length 20. You have your positions are labeled from 1 to 20. So if you have a 0, 1 vector, is the indicator of a subset of from 1 to 20. So you are doing the indicator set of the bases of the matrix. Okay.
Yeah, thank you very much.
All right. So this is the conjectures. Matroid polytopes are Ehrhart positive. Now we understand at least what is the content of this. And so we saw that conjecture and we take it up a little bit. And we say from this polyhedral point of view, and also for some reason that I'm going to talk later, we believe that the right level of generality is that all generalized permutohedra, as long as they have integer coordinates, they are Ehrhart positive. Okay, so this is an example of something that is a generalized permutohedron that is not a matroid polytope. So this is really fitting in the larger conjecture. So let's call it, yeah, so for matrix and for generalized permutohedron in general. Okay, so this is work from the last 20 years. And this is what we started with trying to solve this. As often happens in math, we went into the forest trying to prove this, and we ended up in a different place. But this was the motivation, and I'll come back to these conjectures at the end. So how can we prove something like this? Well, actually, we changed these questions about whether these coefficients are positive implicitly. Is not just because being positive is interesting per se. Implicitly, this is asking, what are these coefficients? Can we compute them? Is there a formula? If they are positive, is there an interpretation? So this is at the end saying, study these coefficients. What are these coefficients? And one way to study these coefficients in this polyhedral context is the following. So there is something called a McMillan formula, or people call it exterior formulas, or some names. But the point is, there are some really interesting formulas that that compare the number of integer points of a polytope. That's what I mean, the cardinality of the polytope. And the formula will look like this. For each face, we are going to have the relative volume of the face, which is a positive quantity, and with some, let's call it a correction term, an alpha term. So each face is going to contribute its volume, which doesn't need to be an integer, and certain correction term. And when you add over all faces, you get the number of integer points. So it's a very interesting relation between integer points and the volume of all of the faces. So this is kind of a surprising formula. Of course, we want these alphas, they are not arbitrary. We want them to be local in the sense that they only depend on the normal fan of f at p. For a given polytope, these are just numbers, so you can always cook them up a way for them to, I mean, you always have all of these volumes, you can multiply them together in order to get whatever you want, the number of integer points. But the idea is that there is some logic to these alphas, and they should only depend on their normal counts. So this formula, the fact that this is possible, this dependence on normal counts was proved by McMillan, but in a very indirect way and very non-constructive and non-unique way. So we are going to use these relations between volumes and integer points, because if we just look at the faces of dimension k, we get the coefficient k of the Ehrhart polynomial. So this coefficient that we want to be positive is okay if these guys, we can compute them, at least in theory, by using this formula. And this relative volume doesn't really matter what it is, but the point is that they are positive. And as long as these alphas are positive, then everything will be positive. But again, it's not about positivity, it's about what are these numbers? Where do they come from? So let me quickly go over one example. So this is the regular permutohedron with length 4. So we have all 4 permutations of 4. And in this case, this formula is saying that somehow each face is going to give us the relative volume together with a coefficient. So for example, the hexagons is giving us a relative volume of 3 together with a coefficient of 1/2. This alpha is 1/2 in this case. And the edges, there are like 2 types of edges, roughly speaking, like a short one and a long one. And they all have relative volume 1, but their alphas are these mysterious quantities 11/72 and 14/72. And this is what we want to understand at the end of the day, is what are these alphas? How do we compute them? What can we say about them? Okay, so okay, so that's the point. What are these things? And we want to compute them for all generalized permutohedron. There are very few examples in which these numbers are known. It depends on more things, because there are several constructions for these alphas. So starting for, there are I would say 3 or 4 known construction, but even for all of them, it's hard to compute them theoretically to know what they are. In very few examples, basically in the simplex, in cubes, stuff like that, this will be the first non-trivial example of revealing what these numbers are. So let me tell you some previous work. So we had, in principle, if we are thinking of this conjecture, we need to do it for all generalized permutohedra, all faces and all generalized permutohedra. But it turns out that it's okay to just look at the regular permutohedron. So all of the generalized permutohedra are elements in the type cone of the regular permutohedron. So this is kind of like, we can maybe prove something that at the same time for all of them, if we can do it for the regular permutohedron. And we also knew that under certain symmetry restrictions, it doesn't really matter how you compute these alphas, because there are different ways and they feel different, but as long as there is certain symmetric condition, all of them have to agree. So only with existence and properties, we can say something about these numbers. This was work 3 years ago. So I'm going to say symmetry many times. It's going to be highlighted because that's really important in the shortcut to compute everything. So yeah. And the main thing, the main new result is that now we have a combinatorial formula for these numbers for any symmetric construction in the regular permutohedron. So in principle, we know what are these numbers for all generalized permutohedron. And these numbers are given with a very specific combinatorial formula. And these numbers, in a way, we're giving a formula for different constructions. So one was given by Berline and Vergne. That is very recursive. The computer can do it, but it needs Barbinok's decomposition algorithm, unimodular decompositions. It's very recursive. It's complicated. And there is another construction by Pomersheim and Thomas, which is more related to what we're going to do later, trying to compute some canonical way, standard way of computing the Todd class. But in any case, if you use any of those constructions, you are going to get some values that we get a formula for them. This formula allows us to compute examples in Sage because it's a very combinatorial and very direct formula. And we found out that these numbers are not positive. So we cannot prove the conjectures in this way, but this does not falsify the conjectures. We know of examples in which these numbers are negative and yet the corresponding Ehrhart polynomials are always with positive coefficients. So this does not falsify the conjecture. This method is not going to work, sadly. So our formulas look something like this. So a formula is kind of complicated, but it's very combinatorial. It's combinatorially complicated, but it's direct. It's a sum over a bunch of diagrams or something that we call a spider diagram. So for each diagram, we consider well, certain restrictions, and each diagram has certain weight, and we just add over all weights. And that's the combinatorial nature of this formula. Previously, there were some recursive formulas or formulas in terms of other complicated objects, but this is, I will think, like this really is a combinatorial formula that Sage can compute in a much faster way. That's like the main gist of this. And how did we do this? Well, it turns out that we had to import from algebraic geometry. So the way we did this was using the theory of toric varieties. So this can be a bit of a black box if you haven't seen this before, but basically you can always associate a toric variety, so some geometric object, to any polytope. And this variety has there is some intersection theory in it, cohomology ring or Char ring, and we can compute something called the Todd class. And this thing being an element there are some results known that certain torus invariant cycles generate this ring. So any element, in particular the Todd class, be it an element, you can write it as a combination of these guys that are generators. They are not a basis, there are relations between them, they are not unique and so on. But the point of doing all of this is that via some intersection theory arguments that are non-trivial, but these were well known in the beginning of the toric varieties history. So this is all of this is already known in Danilov's survey from the 70s. So if we could compute the Todd class, these coefficients that we get using this generating set will give us, at the end of the day, one way to compute these alphas. So there is a connection between this high-level abstraction and the very concrete problem that we are looking for. So if we can compute this Todd class, we can compute some alphas. And again, as long as they are symmetric, they will all agree with the ones that we are looking for. So that's more or less the name of the game. We're going to compute this in some way, then we're going to make sure that this thing is symmetric, hence it will agree with what we are looking for. So let me just quickly say, yeah, so this is a variety for the regular permutohedron. This has some geometric meaning as a, you can find this in a very concrete succession of blowups of the projective space, but things become very concrete because we are not dealing with this in a general level. We are dealing with one particular variety. So we are dealing with one particular ring that is very combinatorial. We have one variable, so it's a polynomial ring, one variable for each subset, and some relations that are, if you multiply two subsets, two variables corresponding to subsets that are incomparable, you should get 0. There are some other linear relations stating that any time that you add over all elements containing, all subsets containing a particular elements, all of these linear forms should be equal. So this very specific ring, we do computations on this thing, because then the definition of Todd class is something, so I will just put it here quickly, but whatever it is, we can start, so it's defined as a product of some series. We can start multiplying and using these relations to compute it, to give some formula with some caveats here. So we are gonna get some monomials, and this monomial will have to be made into a square free by using the relations. And we also need it to be symmetric because we are looking for something symmetric. This is the third time that I say symmetric at least. And after doing all of this thing, we can find a formula for this. One of the surprises, again, because we had a different motivation, we ended up working on this more geometric aspects, is that we can prove that it's not only that this symmetric way is not always positive. So we have a formula, and it turns out that it's not positive, but there is a more general, a more negative statement, and it's that this class is not effective for d bigger than 24. Meaning that symmetric or not, there is no way to express the Todd class as a positive combination of the torus invariant cycles. This requires some extra arguments, but this really means that these conjectures or this positivity is not going to come from a different, clever way of writing the Todd class, because it's simply not effective. This is a surprising result, at least. I was expecting it to be positive, but sadly it is not. And to finish, let me just reiterate that the main motivation for this was the Ehrhart positivity conjecture, which again is something about enumerative combinatorics, and that thing is still open. This does not falsify that. There are explicit examples in which these alphas are negative, and all polytopes with that, those alphas are positive anyway. So this is not saying anything in that direction, anything negative. And actually, we have in this same project, in the same paper abstract, we prove that the linear term is always positive. And independently, Katrina Hachenko and Mohan Ravichandran, they also proved that the linear terms are always positive. It's also surprising because, I mean, to me, this is positive evidence. There are reasons to believe that the linear terms are like the more complicated ones, because this depends on the normal cones, and in the normal cones, those are the cones with higher dimensions. Also the vertices, but the vertices are easy because by symmetry, all of them are the same. So that's kind of like an exception. But the edges should be the next complicated fact. And if they are all positive, this seems to be good news, at least on the main conjecture. And on the matrix case, at least very recently, Luis Ferroni proved that hypersimplices are Ehrhart positive, which means that uniform matrices are Ehrhart positive. And surprisingly, this was not known. This is something that a lot of people, me included, we were trying to prove. There were formulas, but there was no way to prove positivity. And now very recently, he proved positivity, very nice combinatorial way. And I think even more recently, he has proposed new ideas on how to prove this, at least for the case of matrix. And I think that the case of matrix is as hard as the generalized permutohedral case, because for some reason. So this is my conclusion. Don't want to take any more time. And this is the end.
Wonderful. Thank you for a great talk. So once again, I think we will unshare your screen, and everybody can put in your reaction with one of two choices. So, great talk, or put something in the chat if you'd like to be more specific. All right, and once again, I'll hand it back over to Alejandro Morales, who will moderate the questions.
Thank you, Sarah, and thank you, Federico, for the great talk. So there were several questions on the chat, so let me tell you. So there were two questions by Aditya Khanna. The first one is, does Ehrhart positivity imply anything geometrical? And then the second question is, you had this example that was not effective, and is there any significance to 24?
Okay.
Yeah.
Okay, so Ehrhart
Okay,
positivity implies something.
Mais je parle pas, j'écoute.
Actually, I don't know, and there are. So in the opposite way, is there anything nice that implies Ehrhart positivity? And no, and there is a survey by my advisor Fulio that basically we have found a lot of negative results. So it's not correlated, it's correlated in the statistical sense. It seems to be common, but it's not, does not imply things like being normal, having the IDP, having regular unimodular triangulation. It is not related to, we don't have any nice implications or any nice relation. And so there are a lot of negative results actually on that. On the other, what was your question? The 24?
Is there any?
I know that for 24, so we know that we have an argument that Y24 and up is where we start seeing negative values, but it is also possible that you see negative values before. So there is nothing special about 24, and it may well happen that, so I know that for X6 is positive or 7, so at some point it starts being negative. I know for sure that 24, it could be before, so there is nothing special with 24.
Okay, thank you, Federico. And there's a question by Yuken Song. Is there a similar conjecture if the edges are parallel to roots of other types?
So not informally, yes. I'm always saying the word symmetry, symmetry, symmetry. Well, that's the symmetric group acting, and the argument should be, there should be a very similar story for other reflection groups. So yes, there is something, but yes, there is something related. And if you're looking for a place to generalize it, reflection groups are the right, we really use symmetry. So there should be something very related in other types.
Thank you, Federico. And then there were some discussion, nice questions about McMillan's formula. So one was, if you replace the number of lattice points by any valuation, does it maybe, yeah, does that have a meaning? Does it have, is it related to?
Ooh, I think that's, I don't know. I will be very interested to talk about this. I imagine the answer is yes, but I don't know.
Okay.
But I will imagine that the answer is yes. And
there was a recent question by I forgot who asked, sorry about this, but why in that formula is it easy to see why the formula you get integers, if especially these alphas are
No. So that's the surprising part. The volumes do not have to be integers. These alphas are not integers. There are some fractions, but because everything gets together to the coefficient. Well, the regular permutohedron has the particular property that its Ehrhart polynomial have integer coefficient, but that's very, very rare. In general, that's not going to happen.
Okay, thank you. And there's a couple, so let me ask two more. So Cyril van der Eer asks if people have studied the difference of the Ehrhart polynomial at t+1 and the Ehrhart polynomial at t. To these, is this not really possible?
So people, I mean, no, but I see the point. So there are, when you have a polynomial, there are different bases to expand a polynomial. I'm using the most naive one with the powers of t. You could use powers of t+1, so cubes are now trivial, or you can use binomial coefficients, and this is more related to the H star vector. So yeah, people have looked at other bases, but this in particular one, this t+1, I haven't seen that. That's something that makes sense in my head, but I haven't seen that.
Okay, thank you. And so the question about the why you get an integer was by Jia Wang, sorry. And then the last question by Francois Bergeron is there a nice statement about the probability of Ehrhart positivity? Maybe similar to what you see on.
No, well, there is some interesting. There are a lot of computations on dimension 3. So already in dimension 3, the space of all Ehrhart polynomials is not known. It's not to give a cubic polynomial and decide whether it's an Ehrhart polynomial, a polytope. That's open, but there is a lot of work on that. And I mean, there are a lot of heuristic. It seems like most of them are positive, but even for 3 dimensions, I don't see it. This seems to be a very common thing, but I don't know. And also there is another problem in this computation that the Ehrhart, two polytopes can be combinatorially different and have the same Ehrhart polynomial. So one has to be careful about how you phrase the question. So yeah.
Thank you very much, and thank you for all the thank you everyone for all the interesting questions. And I'll pass it on to Sarah.
Yeah, thank you. What an interesting topic. This has been a great opening day of FIPSAC. So thanks again, Federico, and everybody can show your reaction here on the big picture.
Thank you all
Awesome.
for wonderful reactions.